Thank you. So yes, I'll be speaking about the Faraday instability. And what you see here is a visualization from a simulation that we did. You see a thin a layer of fluid on the bottom, and you see it looks as though it's hollow. You know, it looks as though there's space between the bottom and the surface, but that's not true. This layer is filling up all the way up to those bumps. The first set of people here, can you see my cursor? Is that good or not? You see my cursor?
Yeah, we can.
Okay, good. The first set of people here, these are students who have worked on this. And the last set of people here are the authors of a code that they called Blue, as in code blue, you know, when people are having a heart attack, with which we did the latter part of our simulations. Now, there's always this problem here. If you wait too long, there. Okay, so what is the Faraday instability? It was first seen or described scientifically by Faraday in 1831, and it is merely the vertical shaking of a layer of fluid. And above a certain amplitude, waves form. Below they don't. You can think of it as variable gravity. If you put yourself in the frame of reference of the dish, then it's gravity that's varying, and the hydrostatic pressure is alternating with the gravity. So the same thing that keeps the layer of fluid from doing anything when it's not shaken, keeps it from doing anything when it's shaken, until a certain amplitude of shaking, denoted here by A, causes the instability to waves. And they usually have the standard patterns that tile the plane, that is to say, mostly squares and hexagons. And here's a simulation of a square pattern, one of ours. So there you see it. And so Faraday waves are a pattern forming system like a Rayleigh-Benard convection Taylor-Couette flow. These are all very important, you know, prototypical pattern forming system. And Faraday waves, as I said, were first studied scientifically in 1831, whereas Rayleigh-Benard and Taylor-Couette were studied much later in the 1890s, for 1890 something for Couette, and something like 1900 something for Bénard. Note that these instabilities have a French experimentalist and a British theorist. So that's another way in which Faraday is exceptional. It does not have a French experimentalist. It has the British guy who's doing both the theory and the experimental discovery. So maybe that explains why it was not studied for this many years. You can see that right away after these experiments came linear stability analyses by Rayleigh and by Taylor in the 1920s or so. And then numerical simulations, as soon as computers came along, that you could solve PDEs in 2D around the late 60s, early 70s, and 3D around the 80s or so. Whereas the Faraday waves were explained linearly by Benjamin and Ursel in 1954, so a long time after the Taylor-Couette and the Rayleigh-Benard in the 1920s or 10s. And the first viscous linear stability analysis was done in 1994, and the first numerical simulations were just done, you know, what seems to me recently. Okay, so first let me just say one theoretical thing, which we'll use later. Rayleigh and lambda is the same Rayleigh as before. This is the dispersion relation for gravity capillary waves. So what does that mean? This is inviscid, and what it means is if you have a disturbance with a wave number k. Can you see my hands as I do this? Can people see my hands? Yes, hello?
Yes,
Yes.
So if you disturb the fluid with this wave number, then it will oscillate in response at the frequency omega naught. That's what this means, and that's what Rayleigh and Lamb made this formula for. And those of you who know more than I do about the greats like Steve or Alistair can correct me if I'm wrong. We're going to be using this too sometimes, this relation for Faraday waves, but there it's the other way around. What we talk about there is we we oscillate the fluid layer like that. We impose an oscillation, and which wave numbers are elicited when you do that. So you shake it with omega naught, and you get some K. So that's quite different. And another feature I just want to mention about okay, and what you see from that is that the wave number in the horizontal direction depends on the frequency, and it's not scaled by the height of the layer as is Taylor-Couette and Rayleigh-Bénard. Taylor-Couette and Rayleigh-Bénard, you have a layer like this, and you have your rolls like this that take up the this space here, and their width is about the same as their height, and that's not true of Faraday waves. Okay, so let me go on and say what this first history was. Benjamin and Ursel did the first linear stability analysis in 1954. What is this? This is the amplitude of the forcing divided by gravity, and this is wave number K. And so what inside these, if you put on a shaking that has this amplitude and this wave, if you put it has this amplitude, then you will elicit plane waves with the this wave number. So you see you have a lot of them, but in fact, you mostly have this one here. Okay, and this SH means subharmonic, this means harmonic, subharmonic. And let me do a little demonstration of that. Here's the shaking fluid. Let's see if I can do this. This is subharmonic. So you see that period is twice the shaking period. Up, down, whereas harmonic is the same as the shaking period. Okay, everybody get that? And both seem kind of natural as periods that are elicited. This is inviscid linear stability analysis, and they did this by showing that the Faraday problem reduced to the Matthew equation. They did Floquet analysis, and these are called tongues. And if anybody wants to hear more about that, we can talk about it after the talk. If you add viscosity, this is my work here from 1994, what happens to these tongues? They become round instead of having these cusps on the bottom. So that means they have a finite threshold, and they rise according to their K. So here you see really that you're eliciting subharmonic instability at this K. So this is inviscid stability analysis. This is viscous stability analysis, and this is the first to do 2D numerical simulation with Chen and Wu in 2000, and the first to do 3D numerical simulation was our group in 2009. Okay, and that's pretty much what like what you saw before. Notice that our numerical method gives you not just the position of the surface, but also the velocity field. So here you see these. The velocity that is coming into, now it's going to squish this hill. You know that the height and the velocity are out of phase, and here the fluid is going to rush out when the bump comes down. Something that launched a revival of Faraday instability, mine as well as when I was doing postdoc or visit in Lyon, Stuart Edwards and Stéphane Fauve discovered quasi patterns. For fun, Stuart Edwards was a very imaginative guy. They had a dish made of the shape of France, and these are quasi patterns. I'll tell you about that in just a moment. And then this was followed by a big explosion of interest in these things. These are quasi patterns found by Kudrali, Peer, and Golub in 1998 called super lattices. And hold on, let me, yeah, okay. So what's going on here? Well, I told you about a frequency, a temporal frequency eliciting a spatial one. So supposing you had, instead of a trigonometric form for the shaking, you had the sum of two different frequencies like this. So you're shaking with M omega and with N omega. And this cosine sine business is just a way of saying alpha and beta, different coefficients without changing the overall amplitude. So if you had just the M one, then you would elicit waves at this spatial wave number Km. So this you see as this is pretty much looks like what you saw here, right? And if you had just this one here, that's 90 degrees, so you have only this and none of that, none of the red, you would see a different spatial wave number here. So you might think that you would get from this to this maybe by just moving, but as you can see from this picture, that's not so. What happens as you mix the frequencies is you get other tongues coming down. It's very exotic. These are not supposed to be, by the way, in irrational ratio or anything like that. It's just, this is like 2 and 3 or 3 and 4 or something like that. And as you mix those frequencies, you get these islands, you get these cute things. It's very exotic. So you're mixing. And here you have what's called a bicritical point, where both of these wave numbers are excited well, maybe more like this, are excited simultaneously. Okay, and then the extraneous ones just move up and go away. So you have two wave numbers, Km and Kn, that live on two different circles. Alistair worked on this for a while. We'll get to his name. Of course, having wave numbers on a circle does not tell you what pattern you have. You need nonlinear theory to restrict the spatial spectrum. And that's the kind of theory that people like Alistair did at the time. But I will tell you that in a pattern like this, you see these spatial wave numbers here. This is the distance between two big guys, and this is the distance between two small guys. And those are the K. 2 pi over this, 2 pi over this gives you the Km, and 2 pi over this gives you the Kn, and so that's what you're seeing. And this was, then people went really crazy over this. Arbel and Feinberg, in particular, for the two frequencies, 2 and 3, they found all these different patterns that they give all these names to, SS and DHS and I don't know what. And a lot of people did a lot of interesting work on these things in the years around 1995 to 2012. Now let's go back to single frequency forcing. And here we see the square patterns and the hexagonal pattern. Now, Kittig et al., why are they part of the story? Because Wagner here in Germany, he was the first to make a method, an experimental method, that was able to resolve the surface height in time. So you had the height as a function of x, y, and t. And until then, people had taken pictures or something, but they didn't really have good quantitative data. And now his measurement method required the upper and lower fluids to have nearly equal densities to match their refraction indices and high viscosities. Since then, other groups have invented methods to do this. There's Frédéric Moisy's group in Orsay. There's Philippe Petitjean's group where I am. Are there more? I mean, I have a French perspective. Are there other methods, experimental methods for measuring surface height so well? No, nobody has anything to say. Okay, so they were able to measure it, and thus you could do a with good precision. So you could do a spatial Fourier transform on, say, this, and the spatial Fourier transform of a square pattern is a system of squares. This is the Fourier transform of this, and the spatial Fourier transform of a hexagonal pattern is a bunch of hexagonal peaks. So these are spatial Fourier transforms 2D of those experimental pictures. This code that I'm using was really, it's other people's methods. I code, but only incompressible fluids of one phase. So I really, I know very little about this, but my colleagues did this, and I can tell you the few things that there are. The whole parallelepiped is divided into cubes like this, with one density above and viscosity and another density and viscosity below. So those are fields, the rho and the mu. And the interface is described by a set of triangles. And the triangles influence the velocity via the surface tension. This sigma is surface tension. So they are added to the velocity Navier-Stokes equations just at the boundary. And the fluid influences the surface by moving it, by advecting it. So this is called the front tracking method, and there's a single domain, and that's about all I'm going to tell you about the numerical method. So here I'm just going to show you a picture from the same, the same that I showed you before. This is the square pattern and this hexagonal pattern. So this is rainbow and this is chocolate. So here's the chocolate, this is the hexagonal pattern. And you see how the hills are not so clear, but if you look, otherwise you see 6 things about a center. Okay, so it really is hexagonal. 6, 1, 2, 3, 4, 5, 6. Okay, and that was Nicolas Perinet. He did the first numerical simulations of Faraday waves, and that was with the standard patterns, hexagons and squares. And here I'm going to show you the hexagons in beautiful color, as one can do. This is one oscillation period of the surface, and so t equals 0, t over 4, 1/4 of the period, t over 2, that's when you see the hexagonal structure best, and 3t over 4. So you're going 2, 2, 2. Okay, so that's that. And Nicolas was very determined. And so he simulated the hexagons, and we said, very good, you have the hexagons. And he said, I don't know, I think I'm going to simulate them longer. These things here are 1, 2, 3, 4. That's the same pictures as I just showed you. 1, 2, 3, 4 for the four phases of the hexagonal oscillation. You see these black dots. And this is now just a flat contour picture of these. But he kept going, and you can see if with this big empty thing, if I'm telling you this, it's because something happened, and you can see he was right to keep going. The hexagons disappeared, but it didn't become a flat surface. It became something we called beaded stripes. And I think you can see why we call them beaded stripes. Stripes 1, 2, 3, 4, and beads 1, 2, 1, 2, 1, 2, 1, 2. This red thing is an envelope for this oscillation. So again, these are 4 pictures at 4 temporal phases of a single oscillation. And this thing has symmetry. It has Y reflection symmetry, if you reflect in this line. It has X reflection symmetry, but not quite, because you can see that, how should I say, this thing is pointing to the left and this thing is pointing to the right. Everybody see that? So this is a shift and reflect symmetry where if you reflect in X here, you won't get the same thing unless you go down 1, so that you get the thing pointing to the right becomes the thing pointing to the left. Is that clear? It's called shift and reflect symmetry. And so those are the beaded stripes. But Nicolas continued, because that's his nature. And what did he see? Beaded stripes, which looked as though they were going to stay around forever. They became something different, which we ended up calling quasi-hexagons. You wouldn't necessarily call these hexagons if you didn't see the resemblance with the original hexagons. Here you have a white thing that's surrounded by 1, 2, 3, 4, 5, 6 patches. But you can see it's not hexagonal. It doesn't have that 6-fold symmetry. And these are times over those 4 phases. And as you can see, it's not going to stay the quasi-hexagons. It's going to be beaded stripes again. Here's the beaded stripes, but they're not quite as nice as this. They're more asymmetric. How do you see that? For example, these are big white things, and this is very narrow. Whereas here, this white thing and this white thing were the same, just reflected. But here, this is narrow, wide, so it's not the same. It has lost some symmetry. And then it went back to being quasi-hexagons. And these quasi-hexagons are not the same as these for various reasons. But one big reason you can see is what's happening at t over 4 is here happening at 3t over 4. And you might not think that means anything, but it does. What with the oscillation being imposed, phase means something. 0 means, when you're at the bottom, say. And so 1/4 is 1/4 the way up and 3/4 is coming down. So these really mean something. And so this whole quasi-hexagon thing has a spatial-temporal symmetry where if you go from this picture to this picture, So a different one, t plus t over 2, that's to say from here to here. So you bring this over here. You shift in y, and you reflect in x, you'll get the same thing. So for those who like symmetry, this is very cute. There's a relationship between this one and this one that's gotten by doing this, this thing here, this shift and reflect. And now you might think, what else am I going to tell you? Well, it pretty much stops here. This is the end of that story. I mean, it's not the end of that story, but it's not going to do anything else. And here, these are strobed movies. This is at the phase t over 4. This is the phase t over 2. This is 3t over, 0, 1/4, 1/2, 3/4. So then you don't have this distracting Faraday motion. You just see the basic thing. And this is quasi-hexagons, and now this is beaded stripes, and then it's quasi-hexagons. Here, let's go through them again. These, come on. Oh, oops. Oh, come on, let's do it. Okay, so these are the 4 different phases. Yeah, so you can see what it. Some are moving, some are not. Okay, so now let's do a little bit of analysis of this. This is the domain in which Nicolas calculated the hexagonal pattern. It's a parallelepiped. You might think you can't calculate a hexagonal pattern in something that's rectangular, but you can. And the condition is that the ratio of this length to this length has to be square root of 3. And then you may not see it, but this, and this get together to make another hexagon. So when you tile all this in Fourier space, you will get the hexagonal pattern. Remember, I said a while back, its Fourier transform is also hexagons. So you get something like this. I'm sorry, the brown, this blue, and this black, and then their complex conjugates. So that would be this brown and this blue and this black. Not this. This is not of the same length. And indeed, that is what you have. That's the Fourier transform of the hexagons. The beaded stripes, you might not be surprised, look like this. This is the stripe aspect. Remember, there are stripes like this, and these are the bead aspects. Okay. Then when you get to the quasi-hexagons, it's not really hexagonal anymore, but you've gone back to having some of these. You see that you see a certain amount of asymmetry in that this is like this. This is stronger than this. The asymmetric beaded stripes, again, are like the beaded stripes, but not quite. You see that you have this, and you did not have those before. Then you go to the other kind of quasi-hexagons, and you see that now, instead of these being the strong ones, these are the strong ones, and the other kind of asymmetric beaded stripes. And again, you have not these, but these. So we're going to put all these together to make a phase picture like this. These are the 3 modes of the hexagons: the blue, the brown, and the black. When you have hexagons, they're all equal, right? They're all equal. This one here is this one, the one that's not part of a hexagon. And let me show you him. That's him, 1, 0. Okay, you see that he doesn't live, he's not here in the hexagons. He's here in the beaded stripes, but he's not in the hexagons. So we watch them, and when it stops being hexagonal, these 2 go way down. You keep having this one. That is to say, you have this one, which was part of the hexagon, but you don't have these other 2. So they're way down. Meanwhile, you've gone up here. That's the one that lives here, that wasn't here before. So he's gone up. Now, after a while of this, you have these alternation between, between these 4 here, they alternate in magnitude. This versus this. So you take the sum and difference of this. You're not going to take the blue one. It's not going to teach you anything because it stays constant. So you take the sum and difference of the blue and brown, and you take this other one that's popping up whenever you have the beaded stripes, and you plot that in the three-dimensional plane. And what you find is this. These are the hexagons. You have, you stay there for a long time. That's the accumulation of these dots. And then you go over to here, and these are the beaded stripes. And at the beaded stripes, these two are the same. These are not asymmetric beaded stripes. These are symmetric beaded stripes. So they are here, right? The brown and the black are the same, which they never will be again. They're the same here. And you have a very, there, that's them. And you went up like this, and that's when you did this thing here. The 1, 0 went way up. Okay, so here you are. And now this is the difference. So you keep going black minus brown positive, black minus brown negative, black minus brown positive. So you're doing 2, 2, 2, 2. So you just go back and forth in this kind of butterfly, and those are the dynamics as far as we know. And the question, many questions arise from this. I thought somebody would have solved them by now, but nobody yet. Why is there, well, you can see this is a steady state. It's staying stationary for a while, but there's an instability. This grows exponentially. So there's an instability of the hexagons. What is that? Then this thing here looks like a saddle. So again, it's a steady state, but it's going to do this. So there's a bunch of bifurcation questions. What is the bifurcation theoretic genesis of this behavior? Is there a Hopf bifurcation somewhere? Is there a heteroclinic orbit? Well, how do you describe this? Then, is this, how robust is this? Would this happen in a larger domain? Or is it a property of this single domain here? Because that's what we did. When you saw a bigger domain, it was just repeating the visualization. Then you could say, so is this common in a minimal hexagonal domain? And what about this, the fact that you're competing between squares and hexagons in a large domain? Everybody knows those are the main ones. Is that what's going on here in some kind of reduced, constrained manner? Okay, so a bunch of questions, but I don't have the answers to that. So that's the end of story number 1. I have, I think, 3 or 4 stories to tell you. The others aren't as long. I mean, as I said, I told you about the Faraday waves. This is the first pattern story, and there are a few more pattern stories. So are there any questions? I see there's somebody who on the chat. Oh, I don't hear you, Alistair. I see that you're talking. Okay.
Sorry. Yeah. If you're inviting questions midway through,
yes.
You mentioned a larger domain. If you think of those 6 hexagon modes, and the one that's coming up to get involved is like sitting halfway between 2 of them. Mm-hmm. Presumably, if you did it in a big domain, you'd have the ones halfway between the other 2 and the other 2. So all 6 extra ones could well get
this one here, and which are not presently part of the grid.
Yeah, that's right.
Yeah.
Is that possible?
Yeah. No, that's true. That's true. That's a pretty fundamental thing about going to a larger domain. That's true. That's true. You're saying that this kind of rectangle kind of selects for having beaded stripes. Mm-hmm. Yeah. Because it could, because this has a status that these others don't. Yes. Mm-hmm. This has a status that this and this don't.
Avenue for further exploration.
Right. More? No.
There was a question in the chat about resolution. Does it depend on resolution?
I hope not. Yeah, I hope not. Is that a sufficient answer?
It was Ono who asked that.
Yes, it's a couple hundred points in each direct.
Did that answer you, Ono? Was that?
No, I mean the obvious check is to double change the resolution, and has that
that's right.
Whether the times of the transitions change. That's
yes, that's right.
They are robust in that sense.
I'm sorry, say again.
So the transition times are robust with respect to resolution.
Yeah. That's always an interesting question. Even I mean, if there is a heteroclinic orbit, we know that there are instances. Okay, I say heteroclinic orbit, but we know that in finite resolution, we never get real heteroclinic orbits. We only get close to heteroclinic orbits, and the distance that we're at Does that depend on spatial resolution or temporal resolution? Yeah, that's an interesting question, even for far less complex things. And I don't know.
Okay, thanks.
There's a whole lot to be, to be done on this. I've told you pretty much everything I know, that we know. And this is 10 years old. So it seems to me there could be at least one more thesis from this, if not more. Okay, so I continue. Here's the next story. Okay, and the next story is a square container. Now, before I told you explicitly that we were just doing one hexagon, or minimum hexagonal pattern, and every visualization that you saw that was bigger than that, it was just being repeated, tiling the plane. Because this was such a successful thing, these authors that I mentioned who wrote Blue decided to write a big thing, a big code. And now what you're seeing, you can see that it's not just one square. You can this is the true domain. It hasn't been repeated. Okay, and now you see what's happened is that this big domain has spontaneously, it's making squares, but it's spontaneously divided into four subsquares, like a waffle, right? Doesn't it look like a waffle? And this one are in phase, these diagonal ones, and then these diagonal ones are in phase. You can see if you go across a line, you'll have here max, 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 min, 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 right? This one and this one are in phase, and these are, okay? Does everybody agree with that? Okay, so that happens spontaneously. And we don't know why that happens either. It's many theses in this. And we went back and in literature, and we saw that this was just done by just fooling around with parameters. Stefan Duetti had seen something that looked like this. This is what he'd drawn, but this was in 1990 at a time when you could not yet measure in the way that, well, of course, the way numerics does, but also the way that experimentalists did. You couldn't do a real Fourier transform. So this is a sketch of something that he saw experimentally, that he observed at quite different parameters. So I have this kind of, it's a kind of anthropic principle that if you see something in a numerical study and you're sufficiently ignorant, as I am, then it's generic. Because if you're not looking for something, if you're just fooling around with parameters, you're going to find things that are likely, right? Unless you're pointing, you have some special parameter choice because you're very, very smart, you're going to see things that are generic. So I conclude that this is generic, just as the other thing I believe is generic in a minimal hexagonal unit. So as I told you we'd go faster. This is the end of story number 2. Questions about story number 2? Okay, story number 3. What about a radial force? What about a radial version? This is, oh, I should have said that this was another postdoc named Yes Kauji. This now is another PhD student named Aliyigo Ebo Adu, and this is a radial oscillation. So this is something that you cannot, that is much more difficult to put in the lab. You have to take off gravity, the one that goes down, and you have to have an oscillating force like that. So people have tried to do this with various kinds of acoustics or magnetics or in space or both or something, but this is much harder to realize in the lab. So we're going to put in an oscillation like that. And so he did the Floquet analysis, and with the Floquet analysis, the plane waves that were in the plane case become spherical harmonics. You have all this stuff. Don't read it, but let's just go straight to the dispersion relation here. And you remember the dispersion relation for the this is Rayleigh-Lamb. We talked about it before. And now this is what you get. You might have thought that K is has inverse dimensions. In planes, wave numbers have inverse dimensions, whereas in spherical or cylindrical, the angular wave numbers are dimensionless. So naturally, you have to divide by r to have the dimensions of an inverse length. So you might think G L over R and then sigma over rho L over R cubed, right? You might think that just following the model of the first one, but no, it's this, and this is something that you can read about in Lamb. And why is this? Because here you're linearizing about something flat, and here you're linearizing about something that already has curvature. A sphere already has curvature, and when you linearize about that, this is what you get. So that tells you already there's interesting special cases, L equal 1 and L equals 0. L equals 0 is obviously a special case. The spherical harmonic with 0 is does not depend on theta and phi. So what it would involve is expanding or contracting a spherical drop, which of course we cannot do if it's going to be incompressible. So L equals 0, you can see why it's a special case. We'll see about L equal 1 shortly. Oh, and but a nice thing then is these K's are not really different from one another. They're only quantitatively different. L's are very different. If you've seen pictures of spherical harmonics, you know that different L's are quite different. And let's look at that. This is now the tongues, the instability tongues. This is forcing amplitude, and this is as a function of frequency instead of the L's, but it might as well be that. And for the different L's, we have different tongues where you have Faraday oscillation. And the inviscid dispersion relation, which is here, as you vary omega, you get these things, L equal 3, L equal 4, 5, 6, 7. And these are the shapes that we got inside these tongues, the 3, the 4, 5, 6, 7. And you can see these changing L equal 3 to L equal 4, the shape is different. This is a 3 sort of shape, and this is a 4 sort of shape. This is a 6 sort of shape. So you can see that it's much more visual from the very beginning just by these spherical wave numbers L. Now I'm going to show you the different L's. This is an L equal 2. This is a movie. This is the, don't pay attention to that. That's all junk. But this is the fluid flow outside the sphere. This is remember I told you that the code has both the fluid and has the 2 layers, just with different density and viscosity here as here. And this is a frequency that elicits L equal 2. So you see it's going from something like a football or rugby ball to a frisbee. So that's called prolate and oblate. And this is the velocity field around it. And so here it's doing that. It's doing rugby ball, rugby ball, frisbee, rugby ball, frisbee, rugby ball, frisbee. And I think you start to see something else. Do you see that the axis is precessing? You see that now it's oriented along this axis. And this is now a current project to find out more about that precession for the L equal 2 case. And we talked about L equal 2. Let's talk about some other L's. The platonic solids, there are 5 of them. What's a platonic solid? It has regular polygons as their faces, and there are 5 of them. It's the kind of math that the Greeks excelled at. The tetrahedron is a set of equilateral triangles. There are 4 of them. The cube is a set of 6 squares. There are 6 squares, and there are 8 vertices. The octahedron is an object made up of equilateral triangles, and there are 1, 2, 3, 4, 5, 6 triangles. And there are, did I get that right? No, I didn't get that right. There seem to be 8 of them. Is that true? 3, 4, 5, 6. Well, it says here, so there must be 8. 1, 2, 3, 4. Yes, okay, there are 8 faces, and there are 1, 2, 3, 4, 5, 6 vertices. So you see this, the cube has 6 faces and 8 vertices, and the octahedron has 8 faces and 6 vertices. It is the dual of the cube. That is to say, if you turn every vertex into a face and you turn every face into a vertex, you'll get the other one. And you see how this kind of Faraday oscillation works perfectly for that. You had a max and you turned it into a min, max, min. If you take the maxima, the bulges, as being like vertices and the minima as being like flat faces, you see alternation between a shape and its dual. The dual of a tetrahedron is another tetrahedron just upside down. You turn this into a face and you have the dual of a dodecahedron is an icosahedron. And there the numbers are 12 and 20. 12 faces, 20 vertices. Icosahedron has 20 faces and 12 vertices. Here are 3s and 4s. This is alternation between a tetrahedron and the upside down tetrahedron. And then this is alternation between a cube and an octagon. The cube you're used to, the octagon perhaps less so, but I think you see it emerging. And that's what we saw. And then the 5, there's, you saw that there wasn't a Platonic cloud 5. There is with 6. This is octahedron going to dodecahedron. And this thing here it has 5 bumps here. It has, let's see, it says D4, but I think it's D5 symmetry. Yeah, D5 is what it's supposed to be, this one here. So it should be D5. So this is the one that the 5 turns into. And so this is all very pretty. And now, but notice we did 2 and 3, 4, 5, 6. We didn't do 1 yet. Anybody want to guess what 1 is going to do? Remember, I said it was kind of special. So take a moment and think about it before I show it. Ready? Here's 1. Boing, 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 boing. You know, it makes perfect sense. You have positive, on one side you have positive, yeah, you're going this way and then that way, like a dipole. Okay, and it's not changing shape. And indeed, it doesn't work for capillary waves. It's only a gravitational force that can do it. Capillary would require curvature, and so it would require change in shape, and the shape is not changing. So that is now story number 3. So let's go to story number 4, which is another pretty short story. This is now experiments done in my lab, and this is one of the few times that we actually aimed at experimental parameters. And so in 2016, they saw a basic square pattern, and just shaking, they saw it become modulated like this with waves. You see the waves on this square pattern, and here is the film. This is strobed at the Faraday period, so all you're seeing is that wavy stuff. If it weren't strobed, you would see those white things become black and black become white, but you see it's now you just see the motion every capital T. So you see just that one. So we set out to try and reproduce it, and we did. That's pretty much, there it is, it's doing its thing. We pretty much did. We had to change the viscosity to get it, but the experimentalist says that he could well have gotten the viscosity wrong, that fluids age in time. And while doing this, we found lots of other nice patterns like this. The wavy squares you've seen, we've got tilted squares, we've got sort of rectangles, we've got hexagons, or not exactly hexagons because this doesn't have the square root of 3 factor you need, so it's almost hexagons. And here are the spectra. So this is almost a hexagonal spectra. It's not exactly, you can see these are slightly different, both in length and amplitude. The rectangles, their spectra look like this. It's rectangular mostly. These are square. This is squares, and then these are harmonics of the squares. If you add Fourier wave numbers, you have this plus this equals this. So it's natural for nonlinearity to give you these red things. And these tilted squares, it's the same as this except rotated. And the wavy squares, you have this square, and then you have this is what gives you the modulation. These two, they're small wave numbers because it's a large wavelength modulation. And if you watch it evolve in time, it does all this cute stuff with all the modes going crazy. And I think that's, oh no, that's not quite the end. I just was going to give a little advertisement to my colleagues who did this code blue, and they did all this fancy stuff. I say it's tested to 131,000 threads, but that was, I think I made this slide a year or two ago. By now they must have 10 times as much. That's their big thing. They get the biggest computers and they show that it works and scales there. And they're always adding new things. They're adding boiling, and they're adding, I don't know what else. And yeah, this is all the kind of stuff they do, phase change, this, that, the other thing. And they've worked a lot with, this is one of their tests with a splash. That's apparently one of the test cases that that the people who make up these codes do. And this is one of their fanciest cases. They work a lot with Omar Matar, who's in chemical engineering at Imperial. Maybe some of you know this. This is not the resolution. Each of these little blocks is an 8 by 8 by, no, is the 32 by 32 by 32 block. So you can see how huge this is. They have this atomization. And so when they do Faraday waves with me, that's really not demanding of their codes. This is the kind of thing that's demanding. And now I'm finished with all my stories. Thank you.